Yeah, so thanks for being here. What I'm going to tell you about is recent work we have been doing in the context of a group field theory formalism for quantum gravity. So we'll first of all introduce the basic ideas of this formalism, and I will introduce it from the point of view of loop quantum gravity. And next I will discuss how we are trying to address the problem of the continuum in this context, and in particular how we are developing renormalization group tools and renormalization group analysis of group field theory models. And then the other side, the more physical side of the problem of the continuum, is the extraction of effective physics, effective continuum physics, and I'm going to present some ideas about the extraction of effective cosmological dynamics from these models, although you have heard already a talk on the first day from by Stefan. So, first part. So I first introduced the general formalism. Group field theories can be defined basically also independently of any quantum gravity as a new type of quantum field theory. So there are quantum field theories on group manifolds, actually on several copies of a group manifolds, the basic dynamical variables therefore being a complex field on the group manifold. And this is the initial phase space. Depending on models, you can then try to reduce to subspaces of that, depending on the type of physics you want to try to encode. And the number of copies has to do with the number of space-time dimensions you would like to reconstruct in the effective continuum limit, and in a way that should become clear in a second. So in 4 dimensions, so if you're interested in 4-dimensional models, then you have 4 copies of a group, so the field is a function of 4 group elements, or using momentum space, so a Fourier transform, then it's function of Lie algebra elements. The interest, of course, is not in the general framework, but in specific models. But staying at the general level, what is still true is that you build up the theory out of a Fock vacuum. Your Hilbert space is a standard Fock space, where in the initial vacuum you have created no excitations, so there is nothing, no topological, no geometric structure. And when you start creating excitations, a single quantum would be the first one you create, and it has a graphical representation. Again, it should become clear in a second why this is a good representation for the degrees of freedom, as a vertex of a graph labeled by, with external links coming out, and each labeled by a group element. Dually, you can think of it as a fundamental d-1 simplex. This is again the 4-dimensional case. A generic quantum state, if this is the graphical representation of a single quantum, can be represented as an arbitrary collection of spin network, graph vertices, including those in which you glued the vertices to form generic graphs, or as a gluing of simplices to form triangulations. So these are many particle states in this field theory, many quanta states. So your model will be defined by some classical action with some quadratic term, a kinetic term, and some higher order interaction with convolutions of the fields. Now, the main point, the main peculiarity of these field theories as field theories is the combinatorial non-locality here, in the sense that the way you convolute field arguments in the interaction is non-local. You convolute some elements of one field with some elements of another field, and so on. So this is not what you would do in a standard local field theory. In particular, I give you an example. Suppose that you are interested in a simplicial setting, so your quanta are d-1 simplices. I'll give you an example. So I'll give you an example of what I mean by non-local. And by non-local here, I mean that I have to keep track of each argument in the field, so that the vertices of interactions are not actually vertices of a graph with just one line of propagation here interacting joined at a vertex. I have to keep track of each individual argument of the field. If I was just identifying the 4 arguments of one field with the 4 arguments of the other one, that would be standard locality. If this was a field on R4, I would just need to draw one line joined with another line at a vertex. That would be the identification. It's just a combinatorial notion. There's no space-time here. So these are fields on a group manifold. I'm going to tell you what is the connection to space-time physics and to gravity in due course. These are not defined on a space-time. The group manifold is not space-time. So if you know about matrix models, you can think about this as a generalization of that. So at the quantum level, you first try to define your theory in perturbative expansion around the free one. And the peculiarity of the interactions results in a peculiarity of the Feynman diagrams, which are dual to, which are represented as stranded diagrams and are dual to cellular complexes of generic topology. So if you just glue together this type of vertices, even if they're dual to d-dimensional simplices, arbitrary gluings will give you arbitrary topologies. The other general fact is that the Feynman amplitudes, which encode the dynamics of the theory, can be written equivalently either as spin-form models, so models for evolution of spin networks, so graphs labeled by this group theoretic data, or as lattice path integrals. This is also generic. Again, the interest lies in specific models, but this is generic. Okay, so as I said, this is the general definition of the formalism in its basic elements. You can arrive at the same formalism from matrix models to tensor models to here, but I'm going to follow to give you more about the connections to loop quantum gravity and spin-form models, because they give more clear geometric meaning and physical intuition about what we are doing with them. So let me tell you in a nutshell what is the relation to loop quantum gravity. So the Hilbert space of these field theories are Fock spaces, but you can see you can see a generic state in loop quantum gravity that would be a spin network associated to a graph with labels, group elements on each link, as a sort of a many-body state in which the individual quanta are these vertices labeled by group elements that you glue together to form this collective structure. So this is just the intuitive picture. How you technically do it is explained here, but at the point is to say that for any state in the standard Hilbert space in loop quantum gravity, you can find a corresponding state in the Fock space of the group field theory, in which you reinterpret a spin network state as a many-body state. Okay? So that's the basic idea. Of course, this embedding comes with several differences. In particular, in one word, you have to change a little bit the perspective. There is a lot of conditions you will impose on this type of states coming from the canonical quantization of gravity in the continuum that you do not have any special reason to impose here, and in general will spoil the Fock space structure. Because it's the simplest in this case. And it's the simplest if I was just thinking for general principles, but the point is that all the models we actually know at the moment of group field theories rely on the bosonic statistics. Mm-hmm. Yeah. Yeah. Yeah, this stage is all fine. I can tell you that there are models where we have hints that a braided statistics could be another good choice, but let's not complicate the story here. That's not the part I want to discuss, but I can answer questions afterwards. So for now, take it as an assumption of simplicity compatible with what we know about the models we are interested in spin foams and LQG, but indeed you can consider other possibilities. Okay, and the other thing is that loop quantum gravity has a covariant version that has been developed in recent years. It's called spin foam models. And you can think of spin foam models as just histories of, you can think of spin foams as histories of spin networks. So a spin network is a graph labeled by algebraic data. A history would be a two-complex labeled by the same algebraic data. And an assignment of a covariant amplitude is an assignment of complex weights to each of the elements of the complex, functions of the representation data, the group theoretic data assigned to them, and you sum over them for any given complex. And then you have to consider all possible complexes because they are all possible histories of such spin networks. The group field theory completes this definition by giving a prescription, an organization principle for dealing with all these complexes. And the prescription is simply that for any given spin foam model, there is a choice of kinetic and interaction kernels, therefore a choice of group field theory action, such that the model you were interested in, the spin foam model you were interested in, arises as the Feynman amplitude of this group field theory, associated to the complex itself arising as a Feynman diagram of the field theory. This is again generic. Okay. Now, just 2 words about how we construct interesting models. Up to now, most of the work has gone in the direction of, in a direction inspired by the formulation of gravity as a constrained BF theory. So, BF theory is a topological field theory, and I'll show you here an example of how you write a group field theory model for BF theory in 3 dimensions. And in higher dimensions, you add constraints to the GFT formulation of topological BF theory to obtain the gravitational counterpart. That's the strategy. So in 3 dimensions, BF theory is first-order gravity. And a model would look like this. So you take, this is the Euclidean case. So you take a function of 3 copies of SO3, the local gauge group of gravity. That's your field. You impose a gauge invariance under the diagonal action of the group. And what you can show is that the corresponding action, being just a bunch of delta functions as kernels, so which imposes that here you have a 3 simplex, a tetrahedron, as interaction, and your basic building blocks are triangles represented by the fields. So you write down a very simple model in which you only have delta functions as kernels, and what happens is that the Feynman amplitudes take in group variables the form of the lattice gauge theory formulation of 3D gravity, in which you just impose flatness of the holonomies. But you discretize the theory on a lattice defined by the Feynman diagram, just as you would do in Yang-Mills, with parallel transports of the connection. In group representations, this is the Ponzano-Regge spin foam model for 3D gravity. And in Lie algebra variables, which are all just change of variables of the same amplitude, this is exactly a first-order path integral for an action which is which is exactly the discrete version of the 3D gravity action. So at the discrete level, there is a clear connection to discrete gravity, and this holds for 4-dimensional models as well. Again, the main idea of 4-dimensional models developed over the years is just to impose additional so-called simplicity constraints on the formulation that you have for BF theory, because at the classical level, again, gravity can be written as a BF theory plus constraints. So the whole task is to find the correct discrete version of such continuum constraints and the correct way of imposing them at the level of the group field theory amplitudes. So the main message here is just that a model for 4-dimensional gravity is currently constructed by taking very simple GFT kernels with only delta functions, adding gauge invariance, the thing that introduces a gauge connection, and then adding these additional constraints. Okay, the details are not so important for the following. Okay, and there are a lot of results about the current models and more connections to discrete gravity, Regge calculus, and whatever you can look for at the discrete level, at the level of the complexes arising in the Feynman expansion. That, I would say, is reasonably well understood. The problem is indeed the problem of the continuum. Okay, so here is where the group field theory formulation can be helpful and is an additional important tool to the ones we have already in loop quantum gravity, spin-foam models, and so on, because it allows to translate many fully background independent questions into a language of quantum field theory that is more or less standard. Because, as I said, beside this combinatorial non-locality, group field theories are just field theories on a group manifold with a metric, the Killing form on the group, with the topology and so on. So at least at the technical level, many questions have a more or less standard reformulation. The difficulty, of course, is the reinterpretation of what you get. And I will deal with in the following with these two main type of questions, especially the second one. One is how you constrain quantization ambiguities and ambiguities in the construction of models. I gave you the general strategy, but of course when you try to implement it, you have to make choices. And you want to have them under control. And this translates at the level of group field theory in just the perturbative renormalizability of the models and in the study of group field theory symmetries. These are the two main ways in which, in a field theory, you would constrain all the quantization ambiguities, the construction ambiguities, and so on. For two reasons. One is that renormalizability as a criterion is indeed a criterion for constraining which model can deal with long scale flow and which ones doesn't. So which one you trust over a large set of scales and which one you don't. And here we're talking about models that pretend to be fundamental definitions of the microscopic degrees of freedom. If the microscopic degrees of freedom are really Planck scale, if not sub-Planckian, and you want to trust these models, they have to survive and be consistent over a very large set of scales, up to here. And then is a more technical reason, as I said, is a criterion for constraining construction ambiguities. So this is why you do worry about renormalizability. The second reason is that, as I said, all the connections to discrete gravity we have arise at the perturbative level for these models, in the perturbative expansion over the trivial vacuum. If they're not perturbatively renormalizable, even those connections to discrete gravity would be a bit worrisome. The more important problem is, of course, how to define more mathematically and to control in more physical terms the continuum limit of the corresponding dynamics. And this becomes the problem of non-perturbative renormalization. You want to understand the renormalization group flow over the whole set of scales and the continuum phase diagram of the theory, and extract in some appropriate phase effective continuum dynamics that you have reasons to interpret as gravitational. And please keep in mind that from this point of view, we are really in an analogous situation as you would be in a condensed matter system if I gave you the field theory for the atoms and I ask you what is the effective dynamics of the old system of a very, very large number of those. Sure. Sure. it's I'm not sure what to expect, because the problem of the continuum here is even more basic than that. You want to show that there are quantum states in the theory which have no space-time interpretation generically, that somehow collectively at some point a subclass of states acquire a space-time interpretation that allows you to even talk about, you know, a smooth manifold with a Lorentz invariance in the usual sense. So in the fundamental theory, I'm not even sure how to formulate the question whether the model is Lorentz invariant or not. At the discrete level, I can tell you that we have exact Lorentz invariance in the way of you would have it in a gauge theory, a local gauge theory on each acting on your Lorentz connection on each simplex. But that doesn't say anything about the collective behavior. Well, anything. This is not a parameter you tune to 0. There would be a classical limit. It would be, you know, if you put h bar, then would be the parameter you try to tune to 0 for a classical limit. But it's a different limit I'm talking about. In? Sure, let me get there. Okay, I anticipate the question, but I would like to answer questions at the end. So let me anticipate the answer to this. I mean, you can try to formulate. I'm going to talk in a second about non-perturbative RG flow. If you formulate it for matrix models, the way we formulate it for group field theories, a double scaling limit would look like a fixed point in the RG flow. So I would translate the question into what are the fixed points of your RG flow here, and that's what I'm going to discuss now. Sorry? Part 2. I was trying to get there. So I'm going to tell you what we are trying to do to address the issue of the continuum, and then we see if I answer all your questions or not. So the first thing I want to say is that I want to stress once more the difference between a classical limit and a continuum limit in this type of context. The direction of approximation corresponding to the continuum limit is the direction of taking into account at the quantum dynamical level more and more degrees of freedom. If there was a parameter, it would be the number of degrees of freedom that you're dealing with. And it's very different from the classical approximation. And you expect generically to recover effective continuum and possibly geometric dynamics in the regime of large number of such microscopic non-geometric degrees of freedom. And we know a lot in spin-foam models, as I mentioned, about this classical approximation at the discrete level, but we have to go the other way. We have to understand how this translates in the continuum. And the crucial tool is the renormalization group that we are applying for going into this direction of more and more degrees of freedom. And again, we are taking advantage of the fact that we have a more or less standard field theory formulation for our non-geometric, pre-geometric degrees of freedom. In general, we should not expect to have a unique continuum limit, because when you explore the collective dynamics of more and more degrees of freedom of any interacting system, you should expect that the system organizes itself in different phases. So the question is, what are the phases of quantum gravity in this context? And which one allows a rewriting of the effective dynamics in terms of geometry? So again, there is a problem with consistency of the theory, which is addressed in perturbation theory, and there is a problem of non-perturbative RG flow. So first of all, one thing that holds true for both set of problems: how do you set up a renormalization group flow? What is the scale? And again, here you proceed by taking advantage of the fact that you have a field theory on a group manifold, and you say, well, I have a Killing form, I have a notion of a metric on the group, I can define, for example, a Laplacian on the group, or Laplace-Beltrami operator on the group, and that gives me a clear notion of scale, which is indexed by group representations. technically a standard field theory on flat space, beside the space-time interpretation, is nothing else than a group field theory with a very peculiar local interaction. So here is nothing out of ordinary. What is really important is that you need to have some control over the theory space, for example, using symmetries. What are the allowed interactions, the allowed models? And the main difficulty, at least at the perturbative level, is controlling the combinatorics of these Feynman diagrams, which is much more complicated than the combinatorics of graphs. These are cellular complexes, and depending on the model, they may be actually wild. So most results are in a subclass of theories called tensorial group field theories. And I give you just the main elements. I mean, the technical details are not important. So most of the models that I call tensorial have a kinetic term, which is basically Laplace-Beltrami on the group, up to a mass term, and have interactions that are, well, have a special combinatorial structure. They are colored bubbles, so-called. And they are motivated from the tensor invariance considerations. These are a little bit the analog, if you know about matrix models, of matrix invariance, okay, and the unitary group. Yeah. And even for this class of models, studying seriously renormalizability requires generalizing a lot of notions of standard field theory renormalization, the notion of connectedness, the notion of contraction of high subgraphs, and so on. This is the typical Feynman diagram of a tensor invariant thing. There are interactions which are themselves with the structure, and then there are lines of propagation that you have to take into account. The very notion of contracting a subgraph, overlapping divergence, and so on, has to be addressed with care. For this class of models, there are mathematical tools coming from crystallization theory where you can do it, and we are taking advantage of those. Now I just give you the brief summary of where we are in terms of perturbative normalization. So first of all, we can proceed systematically, and there are many in this class of models, and there are many results, and we are proceeding in steps. We are starting from simpler models and building up in complications, going towards the models for 4D gravity that I just mentioned, where you have the gauge invariance, non-abelian groups, because you usually use the Lorentz group, and you have the simplicity constraints. So first of all, there are a lot of renormalizable group field theory models. We have results for abelian models with and without gauge invariance for different dimensions, 3, 4, 5, 6, and so on. And first results also on homogeneous spaces, where is the first glimpse of what happens with simplicity constraints when you go out of the standard group structure. And then we have proofs of asymptotic freedom for a bunch of abelian and non-abelian models. Moreover, actually, I can tell you that asymptotic freedom seems rather generic in these models. Okay, at the non-perturbative level, again, the problem is to control an infinite number of degrees of freedom, and solving that, finding fixed points, means defining implicitly the full theory, the full path integral, if you manage to get IR fixed points. And recently, we've been approaching the problem using the functional renormalization group a la Wetterich. And again, the strategy is to take this as standard field theories, apply the mechanism. And again, let me just give you a brief overview of the results. And again, we are going in steps. Simpler models, more and more complicated as we manage. And we have both results on compact groups, non-compact groups with or without gauge invariance, at least in simple truncations. And again, we see asymptotic freedom. And we are learning how you have to deal with the non-compact case via thermodynamic limits. And it seems actually that the type of phase diagrams we get are also rather generic, at least in this truncation. And what we see is, for these models, is the Gaussian fixed points with all the attractive directions, so the asymptotic freedom, and we seem to see always IR fixed point of a Wilson-Fisher type. And we have hints, again, in this truncation for these models, of a phase transition between a symmetric phase and a condensate phase, where the order parameter is the expectation value of the field operator, standard symmetry breaking mechanism. I guess they're only hints because we're working with simple models and simple truncations. But why is this hint of a phase transition interesting? It's interesting for the last part, the extraction of effective physics. And the reason is that one direction we've been exploring is that is driven by the hypothesis that the relevant phase of these models where you should look for effective geometric physics is a condensate phase. And let me tell you about this. Again, you have heard about this maybe in more details by Stefan. Let me give you the general overview. So one idea is even before asking which type of phase you need to look for, is the idea that goes under the fancy name of geometrogenesis, is the idea that, you know, the emergence of continuum geometry requires a phase transition for in your microscopic system. And then the more specific hypothesis is indeed that this is a condensation of the microscopic building blocks, your atoms of space. If you want to be speculative, then you take this even more seriously and say, well, if there is a phase transition, does it have a physical meaning? So it's not just a technical, is it just a technical thing that you need a phase transition, or there is a physical process corresponding to that phase transition? And again, being really wild and after many drinks, what you think about is the possibility that this phase transition is actually what replaces the Big Bang. So it's really the cosmological process. In any case, you're led to look for effective continuum geometric physics, NGR, in a condensate phase of the system. And take this just as a fancy motivation, but of what is just a technical problem. And let me take a step back and say, okay, there are 2 points of view you can take on quantum gravity. One is that quantum gravity is just a quantum theory of the gravitational field. You need just to quantize GR. In the cosmological context, this point of view leads to quantum cosmology. You simplify your degrees of freedom, you quantize, that's the theory of cosmology with quantum effects in place. Fine. The other point of view is that quantum gravity is a microscopic theory of degrees of freedom that are not necessarily geometric. And the gravitational field will result from the collective dynamics. So in this sense, space-time is emergent. In the second case, if you think about cosmology, the cosmological degrees of freedom should be coarse-grained, highly coarse-grained degrees of freedom from the point of view of the microscopic ones. And they should be governed by a statistical distribution, not really by a quantum theory of homogeneous geometry. So quantum cosmology should be reinterpreted in this context. It will find different place. And I'll show you in practice how this ends up being actually true. So you would expect cosmological dynamics to be something like the hydrodynamic approximation of a full quantum gravity theory. So another task we are setting for us is to extract the effective hydrodynamic approximation from the microscopic dynamics. Okay, so this is basically restating what I just said. I think I have 5 minutes. 5 minutes. Okay. So you're trying to reinterpret cosmology as the hydrodynamics, and we are taking really the point of view that you would take in condensed matter as an analogy. So let me just say briefly what you would do in condensed matter. In condensed matter, you would go from the knowledge of the microstate to a coarse-grained description in terms of something like a one-particle density by coarse-graining. Suppose that you wanted to do this let me just make one other remark. That you see from this that a point in the fluid, the argument of the coarse-grained collective variable, actually corresponds to a region that contains a very large number of microscopic degrees of freedom, first of all, but also has the same type of kinematical dependence on the variables of a single particle in your microscopic theory. This is by definition of the whole setup. Suppose that you wanted to do the same thing in a gravitational context. So very formally, very heuristically. First of all, you have to rethink a little bit the cosmological principle. I mean, what you want to say is that you can neglect wavelengths much shorter than the scale factor. And this is very similar in spirit to an hydrodynamic approximation. It implies that the degrees of freedom of a local region, you take them to describe the whole system. But they do remain kinematically the degrees of freedom of a small patch. Next, suppose that you, again, want to do this very heuristically, the same thing you usually do for particle systems. Well, the phase space of GR is in the metric formulation, the intrinsic metric, the spatial metric, and the extrinsic curvature at every point. Well, you would have if you had the exact knowledge of this state from a statistical point of view, you would have some probability density in phase space. A coarse graining would be that you sort of integrate out all the degrees of freedom up to those at a point or in your very small region. So this would be your hydrodynamic variable. This is of course just too formal. Less formal would be if you use a lattice to replace your smooth manifold and you coarse grain over all the cells of the lattice to obtain an effective distribution with the kinematical variables of a single cell in your lattice. This is already better defined. In any case, the only message from this is that the basic variable of your hydrodynamic description should be something like a single patch density, with the arguments being the geometric data of mini-superspace. The second general conclusion is that if it arises like this, cosmology would be the nonlinear dynamics for such density. And for the geometric observables, you would compute using this density. Now, this is terribly complicated. This is the problem of coarse graining hollow space-time, actually all of the degrees of freedom of all the microscopic degrees of freedom of a quantum space-time, and this is terribly complicated even for a standard condensed matter system. Forget about background independence and all the rest. I mean, if it was just a technical problem, it would be already impossible. There is one special case that we can take as a test example of what we are trying to do, in which this is actually much easier. And those are condensates, in fact. Because of the special nature of the vacuum in the simplest approximations, the coarse graining is straightforward. In practice, it means that for a quantum condensate, the effective hydrodynamics can be more or less read in the simplest approximation just out of the microscopic dynamics. And this is just how you extract the Gross-Pitaevsky hydrodynamics out of the knowledge of the microscopic atomic field theory. In the simplest approximation, that would be the Gross-Pitaevsky hydrodynamics. So what we are doing in the cosmology, to extract cosmology from group field theories, is to follow the same set of ideas and the same strategy. First, you have to identify quantum states in the fundamental theory for which you have a continuum interpretation. And then you have to extract from the fundamental theory some effective macroscopic dynamics for such states. You don't expect generic states to give you anything geometrically meaningful. So this is the summary slide with the results, and then depending on how much time I have, I tell you a little bit more. But again, I'm only summarizing what Stefan must have already told you on Monday. So we find that quantum group field theory condensate are compatible with a continuum interpretation in terms of homogeneous geometries. Spatially homogeneous. The ones that are fine for cosmology and for nothing else. So as such, they are described by a single collective wave function. Then, following just the standard procedures for BECs, we extract the analog for our quantum gravity system of the Gross-Pitaevsky hydrodynamic equation. Textbook. And then what we end up with is a nonlinear quantum cosmology-like equation for this single collective wave function. So we really have something that looks like quantum cosmology in terms of the kinematical variable, meaning the wave function for mini-superspace data, but with a satisfying a nonlinear equation because it arises as the hydrodynamics of the fundamental system. Okay, there's lots of words that I can mention. How much time do I have? 1, 0? Perfect. So I can skip all the technical details. I mean, some of this you must have seen them already from Stefan's talk. Okay, so I guess I can just conclude. So the main work that we are doing currently, and if I had more time, not now, but yesterday in preparing the talk, I would have actually reported on this work and the difficulties we are facing there and the interesting questions, is to extract, to now take models that we have reasons to trust at the fundamental level, from spin foams or from loop quantum gravity and so on, follow all this strategy and extract indeed the effective dynamics for geometric variables like the volume of the universe to see modifications of the Friedmann equation. We have done already this work for toy models, and we have as a template for how you extract the Friedmann equation, and we have seen already that you can indeed extract the Friedmann equation plus correction from these toy models. Now the real task is to do it for serious models. But what is true is the general setup. The second quantized language of the underlying field theory is an important ingredient that allows us to do all this. GFT condensates are a very interesting subclass of quantum states in the fundamental theory. These are the two main messages at the technical level. And at the more physical level, we really are able to extract cosmological equations from the fundamental models. Okay, thank you.
We have time for one or two questions.
How you would describe, and I would prefer not by words, but by some maybe formulas, just usual Minkowski space?
Minkowski space would be in the approximation that I'm using here for these condensates would be a particular class of a particular state of this, a particular example of these condensate states that has a trivial time evolution that is homogeneous in time as well. So it's a solution of the dynamics that we are writing. So Minkowski space would arise as a special case of a Friedmann-like Friedmann-Robertson-Walker geometry. Sorry? Say it again? I'm not sure. Friedmann-Robertson-Walker is a spatially homogeneous four-dimensional geometry that, and Minkowski is something that is also time-like homogeneous. It's a invariant under time-like translations as well. Yeah. So so what I'm saying that you need for a continuum space-time picture, from the point of view of these microscopic models, you need an infinite number of such building blocks. And in fact, these condensates are superpositions of, well, infinite. At least there should be very, very large number of these building blocks. And these condensates are exactly a special type of such superpositions. So they are a superposition in the fundamental theory of many particle states with growing number of quanta, characterized by the fact that the wave function associated to each of them in the simple approximation is the same as the condensate idea. Now we take this condensate idea to be a sort of a quantum counterpart of homogeneity in space, meaning that the data you're able to extract from each patch, from each local region, infinitesimal region, is the same. So this is sort of a spatial homogeneity. Whether you have a time-like homogeneity has to come from the solution of the dynamical equations.
Okay, yeah. One more question.
So
what sets the scale of the fluctuations in the condensate?
So the scale, the kinematical or the dynamical scale? Because the only dynamical scales here would be the coupling constants of the microscopic model that result in the effective parameter of the hydrodynamics.
But still,
so those are the only coupling constants.
Okay, but the condensate, you can think about it as a limit of very large occupation number, right? So, but it's not infinite. And there is a parameter that controls the deviation of the actual state from this idealized condensate, which in your case would be the equivalent
You're asking
of
for the depletion
continuum
factor.
of the continuum. This is the parameter that will define how close you are to the continuum limit.
Not really. That would be the parameter that defines how close I am to spatial homogeneity. Because the exact condensate would be the one in which all the wave functions for the individual atoms are the same in the simplest approximation. And I can of course deviate from that by having a more involved quantum state. Deviation from the continuum would be whether I have superpositions of only some finite number of building blocks. But this, which I can do as well, but it's in the simplest condensate there's no such parameter because they're really infinite superpositions. I'm not working a fixed particle number here, but we can.
More fundamental, I believe that is the thrust of these questions, to get the space-time itself. Whether you get a space-time which is homogeneous and whether it is patchy, and I clearly see you have a parameter which controls that. But there is a deeper question of how you ever get X, Y, Z, and T.
First of all,
no, but in a condensate picture, there will be fluctuations around that because you don't have infinite number of particles there anyway. I thought that is what you were saying.
Okay, can I answer?
Just quickly.
Quickly. So X, Y, Z, and T, you don't really mean the coordinates. You mean... I see. I mean, you can formulate the issue of homogeneity in purely geometric terms without using coordinates. I mean, I would be very suspicious if the only formulation you have of a theory of space-time is coordinate dependent. You really make measurements in terms of physical systems that you use to characterize your reference frame. You don't use, I mean, you don't measure T, you measure a clock. But okay, great. So first of all, you need, we don't know of any way of formulating space-time questions in pure gravity. Then at the very least you have to couple matter fields for which you neglect back reactions. That's a standard problem in quantum gravity. I mean, it's not, I'm not saying anything peculiar to GFT. I mean, physical questions would require the existence of the coupling with matter fields that you use as reference frames to define your X, Y, Z, and T. In fact, when I'm saying that we are extracting Friedman-like equations, you can do it in the pure gravity model in a very formal way, but the real thing is that you couple a scalar field that you use as a clock, and you have spatial homogeneity, so there's no real way to introduce X, Y, and Z. But you can talk about dynamics only if you have coupled the massless scalar field for which you neglect back reactions and so on, and you neglect any interactions, so that it's just a clock and nothing else.
So let's move on. We have another talk to get through before everybody.